This is a walkthrough of solving for an unknown, problem 12, which involves electricity and magnetism. We have a mass spec, which is an instrument that identifies the ions in a sample. It heats up the ions, shoots them into a magnetic field at high speed. The lighter particles curve in tight circles, the heavier particles curve in larger circles, and you can identify the ion by its mass. So we're going to analyze calcium ions. In this particular instrument, they curve in a circle of radius 4.2 centimeters. So part A is what's the mass of a calcium ion, knowing that the atomic weight is 40.1 grams per mole. Part B involves calibrating the instrument to figure out what the magnetic field is that will turn a calcium ion with a radius of 4.2 centimeters. And there's the equation. And the unit of magnetic field is Newton seconds per Coulomb meter, which is a Tesla. All right, part A. Let's just get the mass of the ion, get that out of the way. 40.1 grams per mole. 1 mole is 6.02 times 10 to the 23 things. So we get 6.66 times 10 to the 26 grams per ion, per calcium ion. Ready for part B? Here's the equation, given, as given. The left-hand side, we just multiply things. Everything's multiplied. The units are going to be coulombs meters. We multiply 2 times 1.6 times 10 to the minus 19th times 4.2. And we get that. We can plug in the mass of the calcium ion, but should we use kilograms or grams? Well, we saw a Newton before, and a Newton is a kilogram meter per second squared. So we have to use kilograms. Here's the conversion. There's 1,000 grams in a kilogram. So now the mass we're going to use is 6.66 times 10 to the minus 26th kilograms. So we plug that in. So far, so good. One unknown, it's B. Multiply out the right-hand side. Keep the units, kilogram meters per second, almost a Newton. 1.33 times 10 to the minus 21st. But we have centimeters on the left-hand side, and we have meters on the right-hand side. They have to be the same. So let's convert this 1.344 times 10 to the minus 16th coulombs centimeters into coulombs meters. There is 100 centimeters in a meter. All right, looks like we're ready to go. We're going to solve for B by dividing both sides by its coefficient. 1.344 times 10 to the minus 20th coulombs meters, like that. Now we have B by itself, which is the goal. There it is. And we can push the buttons on the calculator, and we get 0.099 kilogram per coulomb second. What the heck is that? Is that right? Is that a magnetic field? How can we tell? Well, it's given that a Tesla is a Newton second per Coulomb meter. Are those the same thing? Well, we can take the Newton and make this Newton the kilogram meter per second squared and see what happens. So kilogram meter per second squared, we just put it in. There's the Newton. All right, what happens here? The meters go away, and one of the seconds goes away. We're left with a second on the bottom, and we get kilogram per coulomb per second, which is what we have right here. Kilogram per coulomb second. So we did it right. Those are Tesla. So the answer is 0.099 Tesla, which is about 100 millitesla. That's problem 12.